Now that we can do electron configurations for any element on the periodic table, our next goal is to learn something because we know how to do an electron configuration. It's a silly exercise just to say, well, this is where the electrons are, if you can't know anything about the element by knowing where the electrons are. So this part 4 of electron configurations is, what can we learn about an element by knowing its electron configuration? So let us do a group, okay? Group in the periodic table. I'm going to choose the halogens. And we're going to draw the electron configuration for fluorine, chlorine, and bromine together. All right, so let's look at a periodic table and do fluorine first. All right, so if we look at our periodic table, here is fluorine. Okay, the noble gas that comes before it is helium. We know this is our our S block. It starts numbering with 1, and then 2, then 3. This is our P block, and it starts numbering with 2, then 3. So we're going to be helium, 2s2, 2p5. Okay, so let's write that out on our screen. We're doing fluorine. Fluorine is helium, 2s2, 2p5. Now we'll move ourselves to the next halogen, which is chlorine. If you go to the noble gas that comes before chlorine, it's neon. Okay, and we're going to work our way over till we hit chlorine there. So we're going to go 3s2, 3p5. You notice any similarities that are building out from that? We see something happening that's very similar as we move down the periodic table. Now, when they came up with the periodic table, they didn't know anything about electron configurations. They didn't arrange them with similarities of their electron configurations, but they did arrange them in similarity of their properties. The next element is bromine that we're going to do. Now, at first glance, bromine seems quite different. The noble gas that comes before bromine is argon. We move over to the left-hand side, and we have 4s2. And then we hit the D block, and we have the 3D, and we run all the way across that D block before we get back to the P block, and we have 4p5. Okay? So we see some a little difference here in that there's some D snuck in, but we see 4s with 2 electrons and a 4p with 5. 3s with 2 electrons, 3p with 5. 2s with 2 electrons, 2p with 5. We see some similarities that have built out there. Okay, so now we've done the electron configuration for our halogens. So what is similar of this family? What's similar of this family is that they have the same number of electrons after their noble gas core in the highest N. Okay, so we'll ignore that for just a moment. All right. This similarity that we're seeing here is what causes them to be similar in their chemical behavior. That is why when they arrange them on the periodic table, they put these over top of each other. They said, man, these things react very, very similarly to each other. Let's line them up over top of each other. And now we see the similarity in their electron configurations. Okay? Now, any electron that's written after the noble gas core, okay, this is what an outer shell electrons are, what we call the outer electrons or the valence electrons. Okay? They are electrons that's written after the noble gas core, but don't count filled D subshells. Okay? This D subshell is part of an inner core. The outer shell is the highest N's, and any incompletely filled D's. But since those are completely filled, we would not count them. And those are called valence electrons or outer shell electrons. So those are the ones that are always involved in bonding. The ones that are written after the noble gas core, okay, if it's not a filled D. So we won't count those, but any electrons after the noble gas and that aren't in a completely filled D subshell are the ones that get involved in a chemical reaction. Any ones that are here in the noble gas core or in a filled D do not get involved in chemical reactions, so we can kind of ignore them. We're going to be most interested in the electrons that come after that noble gas core. All right, so a couple questions we have here. How many valence electrons, based upon that definition, do the halogens have? All of them have the same. and all of them have 7. 2 here, 5 here. 2 here, 5 here. 2 here, 5 here. The second question says, let's look at, well, that's not a question, we're just going to note something. We're going to note the group number that comes after the above the representative elements. Okay, so let's look at a periodic table here. What do I mean by representative elements? Representative elements are these elements on the towers on either side. Those are your representative elements. And I want you to focus on the number that is associated with the A's, okay? I'm not going to be really looking at the 1 through 18. I don't like that numbering system. I like the A and B numbering system much better. And if you look at the halogens and look at the number associated with the A, it's the number 7. That number 7 is telling you how many valence electrons. There are 7 valence electrons in those halogens. If I were to pick another family and pick another group, let's say I pick this group here. Every one of those guys will have 4 electrons in their valence shell. If I come over here to this group, this family, they will all have 2 electrons in their valence shell. So we can use that number to tell how many valence electrons it has. This does not work for the transition elements. This does not work for that D block at all. But for the towers on either side, you can know the number of valence electrons by looking at the group number. So for our halogens, they all had 5. I could pick any one of those groups, not the transition metal, not the D block area, but on either tower, and I could do the electron configuration for the elements, and I will see that they all have the same number of valence electrons, and that number corresponds with the number above the group. All right, so the noble gases, let's look back at our noble gases, okay? The noble gases we know is this group right here. What do they all have in common? They have 8 electrons in their valence shell. Well, they don't all have 8 electrons in their valence shell. One of them doesn't. Which one is that? Helium, okay? Helium is just 1s2. It only has 2 electrons total. So it can't have 8 electrons in its valence shell. It only has 2. But all the rest of them will have 8. Let's do neon, all right? So neon would be 1s2, helium's noble gas core, 2s2, 2p, all the way over to here, 2p6, okay? Argon would be neon's noble gas core, 3s2, 3p6, okay? Get into argon. This is neons, this is argons, okay? Kryptons. It would be argon's noble gas core, 4s2, 3d10, have to run across that D area, and then we hit the 3, 4, 5, oops, 2, 3, 4, we hit the 4p all the way across 6. So we see that 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, they all have 8 valence electrons in them, okay? That's that configuration, okay, of NS2, NP6 is what all the noble gases have. That electron configuration is the most stable configuration of all the elements. They love that electron configuration. So elements that don't have this, okay, which is everybody else, if they can chemically gain or lose electrons to obtain this, they will. And that's the driving force of chemical reactions in many, many cases. Not in all cases, but in many cases. It is also what makes those noble gases so stable. They love their electron configuration. They are stable like this, and gaining and losing more electrons will take them out of that stable state, so they don't tend to undergo chemical reactions. Now, we used to call these guys inert gases, meaning they will not react at all. But what we established at some point is, okay, we can force some of the bigger ones to gain electrons, to form bonds, And so we won't call them inert anymore. We'll call them noble. They don't like to be mixing with commoners, the rest of those elements, but every once in a while you can get them to do that. All right, so now what it says there in the next statement is that the elements that are closest to these noble gases, now who would that be? Who are the elements closest to them? Well, let's look at our periodic table again. That would be, do a little of erasing because I've got a mess all over the place. Who's closest to these noble gases? Well, the ones closest to these noble gases would be the family right before it, the halogens, or the family right after. And you're like, oh, there's nothing after it. Well, yes, there is. After 10 comes 11. There's 11. After 18 comes 19. There's 19. So this is the family right next to it if you wrapped around to the other side. It's those guys that are the most chemically reactive, okay? So closest to the electron configuration are going to be the most reactive of the elements because it takes very little energy for them to change their electron structure to become like the noble gases. The halogens would gain 1 electron. They would go from having 5 to having 6. So the halogens really readily can easily gain an electron and do that. The alkali metals, which are the metals in the first period over here on the periodic table, that first group, they only have to lose 1 electron, and they can readily get rid of 1 electron and get this noble gas configuration. So that is why they're the most reactive of the elements. As you move further away from the noble gases, they're less reactive. It takes more energy to get those to react. Okay, so that is why they can more readily gain 1 electron or lose 1 electron to get this noble gas configuration. Okay, so we can do an electron configuration of any element. We did that in the previous lesson. We can see that in a group on the periodic table we have similarities in their electron configurations. This is why they behave similarly chemically. We know that the group number above a group will tell you how many valence electrons an atom has. And we are seeing chemically why the halogens and the alkali metals, which are the farthest to the left on the periodic table, are the most reactive elements because everybody wants to be like this. That noble gas configuration is so stable, and if they can easily get there, it'll be very, very reactive. If it takes a lot of more work with the electrons to get there, it takes more energy to form these, and they're not as reactive. We will continue looking at electron configurations and seeing what kind of information we can gain by knowing electron configurations in the lessons to come.